In this section, we're going to be looking at energy and chemical change and how those two things relate to each other. In this section, I just want to start with some terminology to know. Those are some of the words that are written in red here. And we're going to talk about the difference between potential energy versus kinetic energy and how that's related to chemical reactions. We're looking at the connectivity between energy, heat, and temperature in this section. We're also going to look at determining the amount of heat exchanged in terms of the temperature from one object to another. And we're going to understand exothermic and endothermic reactions. So we're going to look at these things and the different types of chemical equations called thermochemical equations, which involve that movement of and the accounting of the heat energy and thermochemical energy during chemical reactions. And those, another kind of term here, we're going to understand enthalpies and some of the other things that are involved in these types of energy reactions. And where we might see this kind of in an everyday situation, this is the important stuff when we're talking about nutrition and food and how much energy our food contains and how much energy we can get out of it once it's broken down. So these are the processes and the steps that nutritionists will use to understand the energy contents of different types of foods, as well as for chemists to understand different types of energies that are going to come out of rocket fuel, for example, or for the energy that's contained within batteries, maybe in an electric car. There are really two different types of energy that we're going to focus on in this section, and one of those types is called potential energy, and that's the energy stored within a system. So the potential to release that energy. And then the other is kinetic energy, which is molecular movement. So the actual energy that the system has right now in terms of its movement. How do we measure these things? One way that we can measure these types of energy is through work. So the changes in pressure can put work onto another object or move another object, for example. The other way that we can measure this is through heat. If we see changes in the temperature, then that is how we can measure the type of kinetic energy we have in a system. So let's look at this in a little more detail. But first, we're going to look at potential energy. Here's an example of stored energy or potential energy. In, for example, a astronaut is going to fly into outer space. We have these big rockets, and essentially they have a ton of jet fuel in them. And that jet fuel is going to burn. It's going to push off, release energy that's stored in the system to allow this spaceship to fly into outer space. So a lot of stored energy to get this massive amount of equipment into orbit. Some of this energy is based off of normal physics interactions and ideas. One of those, for example, would be like gravity. So the reason that we need energy to push off from Earth is because there's gravitational pull from this heavy metal into the Earth. And so we need to be able to release ourselves from that. We'd have to generate some thrust away from the Earth to break that gravitational pull. Some of these we'll look at are positive and negative charges. So you can kind of think about magnets, those things pulling each other. There's some type of stored energy in those systems. Springs in a lot of pens or mechanical pencils. There are springs in those that will store energy where you can click them down and click them up to change how those things are. Or you can use those springs also for a lot of different purposes to store energy. We store energy in pipette men for those biochemical tools that we use for moving liquids around. Those contain springs as well. And the chemical energy we're going to be talking about, these are more mechanical energies. Chemical energy is the potential energy possessed by chemicals. So when we take rocket fuel and we take oxygen and we burn that rocket fuel, it gives us water. It gives us carbon dioxide. It also will give us a lot of energy out. So the chemical energy is that potential that those molecules have before, for example, they might be burned. And they're stored within the chemical bonds that we are going to make them. And breaking bonds requires energy. So this initial form here, we have hydrogen and oxygen. We're going to make water with that. To break these bonds, these actually requires energy to break these hydrogen bonds. So this is H2. There are 2 hydrogen atoms. Those need to be broken apart. Oxygen atoms need to be broken apart and recombined to form water. Now that initial breaking on the left side requires a little bit of energy. But once there's reformation of the bonds, the formation of bonds releases energy. So it's all about the overall energy, right? So the breaking of the H2 and the O2 does require some energy, but once it forms water, there's more energy that's released than there is used to break these bonds. So that's what we're really going to look at and think about a little further and to try to figure out what that means in terms of the potential energy a system might have. I want you to think about this question. I want you to, kinetic energy is the energy of movement. So I'd like you to make a list of as many different types of movement as you can, and then see if you match up with what I'm going to present here in a second. So just take a second, pause, and think about this question. Now that you've made your list, maybe you can organize these into these 3 basic types of kinetic energy. So there's really 3 that they probably fit into. One is vibrational energy, and that's basically just the shaking and vibration of a molecule. There's a rotational energy where you can have rotation. You can see that compound spinning. And then you have translational, which is just the movement energy. So most of those that you had listed should go into one of those 3 categories. When we're looking at this, very important that you consider that kinetic energy is the same as the energy of movement. Kinetic energy, here's an equation here for calculating the kinetic energy. We calculate this by taking half of the mass of that object times its velocity squared. So that gives us the rough estimate of how much energy is involved. So this movement and the mass of that movement, that's going to give us our kinetic energy. Here's a kind of like a little flash video of this idea of looking at the difference between potential energy and kinetic energy, how fast it's going, and how this all fits together. So here on the first slide, we have this roller coaster that has basically no potential energy. So it's going 0 miles an hour. It's got no kinetic energy. It's got no potential energy. We're going to move it up to, and you can see this moves up. As we go up this hill, we're going to increase the potential energy. As we start to go faster, we're going to increase the kinetic energy. So we're going to go the first step here. And you can see this first step, we get this buildup of potential energy until we're on the very top. And the velocity is pretty low, so there's not much kinetic energy. But then we're going to transfer this potential energy is going to change from potential to kinetic. And we're going to be going faster as we get to the bottom here. Now, as we reach the bottom, we have mostly all kinetic energy and very little potential energy because we're at the bottom of this hill now. And we're going to transfer as we start to step up this loop. We're going to increase the potential as we get to the top. And then as we go back down, right, but we're not way up here as we were in 1. We're a little lower, so that potential energy is not all filled, and there's still some kinetic energy. We're going to move back down, and we're back down to full kinetic energy, and we're going to go back up and get partial kinetic energy, partial potential energy. And so that's kind of that system we're looking at when we're talking about potential energy, kinetic energy, potential, kinetic, potential. So that's kind of the terms I want you to kind of think about when we're thinking about potential versus kinetic, right? Kinetic is movement. Potential is when you put yourself in a situation to be able to have that kinetic energy in the future. And specifically when we're talking about chemical reactions, it's after a chemical reaction. What's kind of interesting about this whole idea is we actually can't know how much potential energy is in a system or in a molecule, for example, but we can measure and determine the kinetic energy. So this number right here, this potential energy in this diagram, we don't really know what that is until we get to 2 and we look at the potential energy. Then we can say, oh, okay, based off of how fast it's moving here, it must have had this much stored in it. So this is one of those things that's kind of interesting, but it's a relationship that we can use to understand what that potential energy was. Here is a kind of word problem that's putting some of this information in context, and so that we can kind of think about a real life situation. So if we have a velocity of this car here, let's say it's 20 meters per second, and the weight of the car is 500 kilograms. So this weighs 500 kilograms. What's the kinetic energy in joules? When we're looking at these, I'm going to just plug and chug these values. The kinetic energy, remember, is half of the mass times the volume squared. So I'm going to take half of 500 kilograms, which is the weight of the car, times 20 meters per second, and I'm going to square that value. And we're going to end up with, once we do that, we should end up with 100,000 kilograms meters squared per second squared. So those are going to be our units. And you'll notice kilograms meters squared per second squared. That unit is actually equal to 1 joule. So when I solve this, I get 100,000 kilograms meters squared per second squared. That converts to the same 100,000 joules. So now that we know that we have 100,000 joules is our kinetic energy here, we can know what the potential energy was at the top, and the potential is 100,000 joules of energy, of potential energy at the top. So we can only figure that out based off of what we saw the kinetic energy being at the bottom. Another important part this analogy can help to show us is that kinetic energy can actually be transferred. So just like these roller coaster cars, if this roller coaster car back here ran into number 6, it's going to bump into it, and this one is going to move because of it. So molecules can run into each other and transfer their velocity and their energy from one molecule to another. So that's an important part, things that actually do happen and will happen in real life, and that energy can be transferred. That's really, we're going to talk about how we can measure heat and measure temperature. That's really kind of what's happening when we're measuring temperature. We have things bumping into each other and they're expanding and changing. So we'll get into that once we talk about temperature a little more. So let's look a little bit more about temperature versus heat. So when we're looking at temperature, that is telling us it's the average kinetic energy means a higher temperature. So if we have a higher average kinetic energy, we're going to have a higher temperature. So you can see here we have these arrows representing how much basically velocity we have, or how much speed that these molecules have. They have a faster kinetic energy. They're going to be higher temperature. Lower kinetic energy, lower temperature. Heat, however, is really talking about the amount of energy that was transferred between objects. So just like that train car, we can't know how much kinetic energy was there, but we can determine how much is transferred. And so that's the heat is the total energy transfer, and it gives us some amount of idea of what that temperature is. I want you to take a moment to read which of these different sentences and determine which one is correct with regards to heat transfer. All right, so hopefully you've had a chance to think about this. And if we're looking at A, heat is independent of kinetic energy of a system. Well, remember that heat is the transfer of kinetic energy, so it's not independent of that. It's directly related to that. For B, heat cannot be transferred. Heat is the transfer of kinetic energy, so that is also not true. So for C, as kinetic energy from A is transferred to B, so A heat is transferred to B, box A gets cooler and B gets warmer, which also means that the molecules in this box are going to have higher kinetic energy, so their average speed is going to increase versus A is going to decrease. So A is going to be cooler, B is going to get warmer. That is the correct one. And basically D is the opposite of that, also not true. All right, so now I would like you to think about this idea here. Based on what you know about heat transfer, think about the best way to keep heat transferring from box A to box B. So how would we keep something from heat from transferring from box A to box B? Okay, so hopefully you've had a chance to think about that. So either place a high density object to act as an insulation or place a low density object. It might surprise you to know that the best way to keep heat from transferring is to place a low density object between to act as insulation. Now this might make more sense when you think about some of the things we use as insulators. So if you have a really good coffee mug or an insulated kind of metal jug, the best ones actually have a vacuum that's pulled in between them. So it's really low density. They've taken out any of the molecules in this vacuum. And what happens because of that, you don't have any compound, any molecules to transfer heat to that then won't transfer to your liquid, for example. You also have perhaps heard of the Yeti coolers. They also pull a vacuum to keep any heat transferring from the maybe cold food that you have in your cooler to the hot temperatures outside. So there's an interesting thing that if we're looking at a thermos with or without the vacuum or without the lining, the lining, sometimes there'll also be a metal lining in there, reflective, and that will reflect out any radiation, anything that's coming in with kind of like sunlight or higher energy radiation that might warm things up as well. You might also think about insulation and think, oh, why do we put insulation in our walls? Because that seems like there's more stuff there than just air. And if you've ever crawled up in an attic or in your basement, you have insulation, and it's always talked to be important to put insulation in there. Well, although insulation does have, there's foams in there, there's some, it is more dense than just air. This is done to actually help prevent air movement. So the moving of air actually helps to transmit that heat from maybe the outside to the inside or the inside out. And so that foam actually prevents the air movement, and it holds that those molecules in place and keeps the molecules from transferring heat from one side of the wall to the other. So that's why insulation has some density to it. It's kind of funny because I was reading one of the cans. I was doing some work at home, and one of the cans of insulation that kind of phrased the foam spray you can get was saying how it was more dense than the other one, which is kind of funny because that would indicate that it would actually transfer heat better. And so that was, it didn't make me want to buy that insulation. But the purpose of the insulation is just to keep from air currents from moving and transferring that energy. So looking at liquids versus solids in kinetic theory, we remember that liquids can, if they're dissolved, they're constantly moving, running into each other, interacting, although it might be happening a little more slowly than they would be in the air. And the particle distribution of gas and liquids should be the same at the same temperature. So the distribution of those kinetic energy in those systems should be similar. So here's some examples, just visually looking at these. If we have hot and cold objects placed in contact with each other, whether it's air, gas, liquid, solid, those hot objects are initially going to be moving faster. Kinetic energy is transferred from the hot object to the cold object when they're put next to each other, and eventually all of the averages are going to even out, and the cold side's going to get warmer and the warm side's going to get cooler, and those overall temperatures will eventually become the same. So this is one little thing that kind of reminds me of something else I do, an actual function of this knowledge, is if you do have, if you like your coffee really hot, or you maybe pack soup for lunch in a thermos and you want that to stay hot, a lot of times if you are pulling something out of your cabinet, maybe it's not really warm yet. So what I do for my kids' lunch, for example, if I put soup in there, I might heat up some water and pour that into the thermos first, so that instead of starting with a cold thermos and then cooling off your soup, you start with a hot thermos, you put hot soup in it, and it will stay hot longer because you're not transferring that energy from the hot soup to the cold thermos and then cooling it down right away. So it just depends. I personally like my coffee a little cooler because I probably drink it too quickly. But I like my coffee cooler, so I generally won't ever do this with my personal coffee. But something to think about, it actually works pretty well to keep things hot for longer. So thermometers actually use this concept of heat transfer as well. When we're looking at, for example, a thermometer, well, typically now they used to have mercury. A lot of times now we're trying to get rid of that mercury and use alcohol. And alcohol will be put into these glass containers, and then when you have heat transferred from the outside environment to the alcohol, that will have these compounds move more, and that will increase the pressure in here, and they'll expand out and take up more space. And that's then how we can tell. And then these pieces of glasses will be graded, where each different tick mark will be, for example, a degree in Celsius or Fahrenheit. And so the more heat that's transferred in, the higher the kinetic energy, the average kinetic energy, and then we're able to look at that temperature. So that's basically how these ideas work with thermometers. Now, this idea also we can put into equation form. So there's this relationship between energy or work, pressure, and volume. So the energy of a system is equal to the negative pressure times the change in volume. And work is really the same idea. So it's equal to the negative pressure times the change in volume. So here's this just listed out. We're looking at pressures, changes in volume. This little delta is a Greek term that means change. So that's the difference in the starting point volume to the ending point volume. So final minus the initial, that's going to be your change in volume. Let's look at some examples we'll look at some examples of this in just a moment here. So first let's define what pressure means before we start to use that equation. Pressure is a force over the certain amount of area. So if we're going to put a certain amount of force over some amount of area. So here's a look at pressure exerted by the weight of the Earth's atmosphere. This is for every inch squared, there's 14.7 pounds of force put onto that square inch. This is also, just for some conversion factors, 14.7 pounds per square inch is the same as 1 atmosphere ATM of pressure, and that's also the same as 1 bar of pressure. So these are different units that are used that mean the same thing. So let's go back and look at this equation where we're looking at the work energy is equal to the negative pressure times the change in volume. So how would we use this equation to solve a problem? So if we have a system contracts by 1.534 liters. So now what does contract mean? It means it gets smaller. So that volume, this is a liter, that is a volume measurement, and it contracted, so it got smaller by 1.534 liters. It's under a constant pressure of 2.134 atmospheres. What is the work that has been done on the system? And here's some little hint here. 1 liter times atmospheres is equal to 101.3 joules. So let's look at this. If we have the negative pressure times the change in volume, so we're going to take this 2.134 atmospheres, that's the pressure, and we make that the negative value, negative 2.134 atmospheres. We multiply that by the change in volume, which, because this was contracted, it's a negative value. It got smaller. It went to negative 1.534 liters. So we have a negative times a negative. That's going to give us a positive value of 3.274 liters atmospheres. So liters times atmospheres is the unit, right? We took an atmosphere, multiplied it by a liter. That's our unit there. Here I give you a little hint that 1 liter atmosphere is equal to 101.3 joules. So I take this compound, the equation of work, and I'm going to convert it to joules, and I get 331.7 joules of work that was done on this system. So one thing I want you to notice is this is a positive value, 331.7 joules. That means that I had to put that much energy in to the system, and I had to contract it to shrink this down. So you can also think of this kind of almost like a spring, right? If I wanted to press down a spring and make it smaller, I'm going to have to put energy into that spring to get it to be a smaller volume. And so that's the same thing here. I'm putting energy into the system, and that's how I'm getting it to shrink. And that also means that this system now has more potential energy, because I've put energy into the system and it's holding that energy, and it's going to easily be able to, if under the right circumstances, release that stored energy and use it for kinetic energy. So we have to look at a few things when we're talking about heat and energy and temperature. So one of the things that we know about heat is that we cannot measure it directly. So it's really looking at the gain or loss by an object, but sometimes there are inefficiencies and there's not a complete, right, from one compound to another that might go into the environment. But there's only a way to look at, we can't really measure heat, the total energy transferred. We can only measure the temperature or the average kinetic energy of a system. So the relationship between heat and the change in temperature gives us some idea of how this works. So this is how we can look at using temperature to calculate the heat. And for these different compounds or these different symbols here, heat is Q, and S is specific heat, and M is mass, and delta T is the change in temperature. This unit here, the specific heat times the mass, is also known as heat capacity. And so different objects are going to have different heat capacities. So if I'm looking at lead versus gold versus silver, they're going to have different heat capacities. So these are the units: temperature, mass, specific heat, and heat capacity. These are the relationships between temperature and the temperature change and the amount of heat that was transferred. So here's some more different ways of looking at this as well. And looking at the total internal energy of a system, if we have one of those components is going to be the heat energy, remember that is the same as the average kinetic energy of that system. And also the amount of work that it's doing. So if we're looking at how much there we have this is moving, and how much of that movement is maybe doing some amount of work or pushing, creating pressure of that system. So thinking of this on a molecular level, thinking of movement as heat, and a large scale, if we're pushing at a macroscopic level, that movement pushing against a wall or a barrier, for example, that would be the work that's being done. The term thermodynamics is talking about thermo is heat and dynamics is movement, so heat and movement. One of the first laws of thermodynamics is that the energy of a system may be transferred as heat or changed to work, but it's not lost or gained. So that means that the overall energy of a system, for that change in energy, has to involve heat and or work, and those things cannot be lost or gained. Just like when we talked about the difference if we have a mass on one side of the equation, we can't lose or gain mass from anywhere. That's what we have in our universe for mass is what we are going to have. It doesn't go away and disappear. It's always going to be present in those fixed concentration or ratios, right? If we monitor heat transfers of all materials involved, we can predict that the sum will be zero. So we have some will gain in energy, and then there'll be an equal loss in energy. So just like mass, if we lose mass from some place, it's got to go somewhere else. And by looking at the surroundings, we can predict what's happening in the system. So looking for those transfers, we can identify what's going to happen in the system in the future. So this is essentially the first law of thermodynamics is Q. Heat is absorbed by the system that's coming in. If Q is positive, heat is coming in. If Q is negative, heat is being released by the system. It's going out of the system. If W is positive, work is being done on the system, or it's going to be compressed, for example. If work is done by the system, it's going to expand out. So that's a negative value for work when W gets larger, for example. When the heat plus the work, if that value is a positive value, that's called endothermic. So essentially if it's endothermic, we're increasing the potential energy, and we're putting energy into the system and storing it into a system. So that means, for example, if we have a positive, if heat is being absorbed by the system, that energy is bringing that energy into the system, so that's being absorbed. So that would be endothermic. Also, if work is done on the system, so if I have spring and I compress that spring, that's a positive W. That's going to also make something more endothermic. The opposite of that is called exothermic. So it's releasing exo, outside, thermic. That would be heat energy, for example. If I'm releasing heat, or if I'm doing work is done by our system, that's releasing that potential energy into these other types of kinetic and or work energy. So that would be exothermic is negative, endothermic is positive. So let's look at this in some real life examples. If we're thinking about a system absorbing energy, that is where energy is coming into the system. This would have a positive sign. So the final energy of that system is larger than the initial energy. And that would, if we took the final minus the initial, this delta E, that change in energy, is going to have a positive value. An example of that would be photosynthesis, where you have sunlight is going to give this plant the energy it needs to grow and to take up carbon dioxide and get larger. So that is an increase in potential energy for that system available for use later. So it's taking it from somewhere else. The opposite of photosynthesis for us would be if we have fat on our body, we break that down, we use that as energy, and then we start to be able to run around or do something with it, right? That's the opposite. And then our initial internal potential energy is decreased as we use that to run, for example, and allow our bodies to move, and we use that for kinetic energy systems. We're looking at this delta E, or that change in energy, is independent of path. So it doesn't matter if, for example, we create heat. So if we have a battery that's fully charged, and if you would connect these two, the electrodes here with, for example, a wrench, that's going to create a lot of heat. That energy is going to really quickly leave this system in the form of heat. So that's going to be a big spark, and we're going to have light, and we're going to have heat coming off of this. And then that's going to lead to a dead battery pretty quickly. So that it doesn't do any work, but it does release a lot of heat energy. Now let's say we have this fully charged battery, and we're going to hook up a motor. And that motor is going to spin, it's going to do work, it's going to make movement. And so that is going to release energy through work and through kinetic energy. And then we fully discharge. It doesn't matter, there's the same amount of energy released. It's just a matter of if in heat energy or work energy. And then obviously if you have a motor, for example, that's what we're always fighting with in terms of efficiency. So you want this all to do work and release very little heat, but there is going to always be some heat that's released. One of the differences between traditional light bulbs and some of the more LED bulbs that we have nowadays, those release a lot less heat. They're a lot more efficient. The light that's coming off of them is lower. It takes less energy and it doesn't release as much heat. So you'll notice if you have an old-fashioned bulb, you have to be really careful when you touch those if you want to take one of those out. But some of the newer LED bulbs are generally not as hot, and that's because they're a little more efficient. They're not releasing as much heat energy, so more of that energy can go into lighting the light bulb actually. All right, here's a question to look at the difference between looking at the changes in energy of products versus reactants, and I want you to be able to read this kind of word problem, figure out what is the products, what are the reactants, what is the difference here, the delta E for this, post this in our Blackboard space, and then we can chat about your answers and what you thought for this question. And in the next lecture, we'll be talking about a different term called enthalpy, and we're going to discuss how to solve problems involving enthalpy and what enthalpy means.